Hello. Is my voice clear to you? Can you hear me clearly? All right. All right. Great. So, were you able to access the SSH now? Some of you were able to connect via PuTTY, and some of you were not. All right. Good. 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 So, this is a very, very important part, and we are. I'm happy to see that you are able to connect. It's a very important thing. Great. 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 All right. So again, good afternoon, everyone. I'm Sandeep Giri. I'm going to take the Hadoop session today again. This is the third session, and today we are going to discuss the MapReduce paradigm. All right. Today we are going to work on few problems so that so that so that we are able to convert any problem into MapReduce, and we are able to think in terms of maps and reduces. Okay, this is a very important aspect of distributed computing, and MapReduce has been a fairly successful paradigm. Okay, and not only because MapReduce is the only solution, but MapReduce is used even in the newer applications such as Spark, and MapReduce is also used in the non-Hadoop kind of databases such as your MongoDB and other databases as well, CouchDB as well, right? So MapReduce as a paradigm is not only specific to Apache Hadoop, but lot of other components have also absorbed this functionality. They have also implemented this functionality because they found that MapReduce is the very important paradigm for any computing. Okay, MapReduce is sort of a logic kind of thing. The way we say that this is a for loop, this is a while loop, this is my if condition, this is my case statement. Similar is the construct of MapReduce. If you think in terms of the paradigm or construct, it is that way. All right. So did you think about this problem? If you have a plain text file of all of the Lord of the Rings books, say 1 MB for now, let's assume for 1 MB, how would you find the frequencies of words? Okay, you have a plain text file which contains multiple words per line, and this is a huge file in terms of plain text. It might be 1 MB to 5 MB, some sort of thing. And if you see that 1 MB is actually quite huge, right? So how would you find the frequencies of words? So is the problem statement clear? If in real life somebody gives you this assignment, what are you going to do with it? Okay, what is it that you're going to do? What will be your approach? Frequencies of words, as in frequencies of word means that there would be few words which will be repeated many times. There will be few words will be repeated less time. So we want to find out each word and its repetition. How many times a word has been repeated? Okay. Okay. So Chaitra says that it is going to be a regex p count. All right. And read line by line, split into word, and save it in a hash map. Okay, that's good. That's good. We can get the number of counts for the particular string. Okay. We give, yeah. Let me just take your solutions out. All right. Let me just take your solutions out of the window. All right. So we can get the number of count for the particular string using regex p count. Yeah, but that is searching for a word. I'm answering to Chetra. Chetra says that using the regexp underscore count, we can count the number of words for a particular number of counts for a particular string. Yeah, but that is like saying control F and then finding out the how many times a word has occurred. What we want is we want to do the thing for all the words in the input text. Okay. Read line by line, split into word, and save it to the map. That was fine. This is good. I can use I can use a hash map. Key as the word, and key should be unique. And value is counter frequency of that word. But I feel it's not suitable for big data. Okay, okay. I would like to understand why do you feel that way? Okay. Okay. Pratik says that using Java program, we can split a string on the basis of spaces, then can enter the words excellent, excellent. So we have got sort of two approaches. I mean, these are same approaches actually. Okay. Any other approach? Any other approach? Using wc command to find the number of files. Mhm. Give me a little more details because wc command of Unix. wc command it does not give you the word count of the it does not give you the frequency counts. It gives you the total number of letters, I mean total number of characters in a file, total number of words, total number of words in a file, and total number of lines in a file. WC will not give you how many times a word has occurred in a file. So if somebody gives you this assignment other than this Java approach, what all approaches will you take? Excellent, excellent, Chatra. We can use group by in SQL, right? Yeah, but for that you should have one word per row, right? You should have one word per row, and then you can do a group by in SQL. Excellent. Keep that in mind. We will talk about it, and you'll find that how close you are to the actual solution. Okay. Excellent, excellent, Sashikant. Thank you. So collection dot frequency does the same thing as, you know, for each key, it's I think it gives the frequency. I haven't used this particular method so far, and I didn't even know that this collection dot frequency method exists. Good. So I got to learn something. I'll have a look at it. Collection dot frequency is something I need to look at. All right. Now, okay, okay, this is good. Collections dot frequency. Okay, yeah, it's a static no, it's not a static method. All right. Any other answer to this one? Now, so I was exactly waiting for this approach, what you have given to me. Okay. Basically, create a frequency or hash table or map or hash map or howsoever you want to say. It's a sort of a dictionary where where key is our key is the word, and value is the number of times that word has occurred. Okay, so we pick up word by word from this file, and then we check if it already exists in the dictionary. If it does, then we just increase the count. If it doesn't exist in the dictionary, we add this as a new key and put the number. So that was the approach almost all of you have given. Okay, whether you use collections dot frequency, that also does the same thing. Okay, and okay, so the only difference between the collections dot frequency is the summation of total number of keys is done by this. Okay, yeah, right. So now my question to you is my question to you is do you see any problems in this? In this approach, we are putting the data into memory. Hash table is in the memory, dictionary is in the memory. We are putting hash table into the memory, and as and when we encounter a word, if it's new, then we add it in the dictionary as a key and the value as 1. And if it is already in the dictionary, then we increase the value from 1 to 2 or 2 to 3 or and so on. Whatever value is there, we just increase that value by 1 and save it back. Right? This way, we keep on we built a dictionary. So this dictionary or hash map or hash table or whatever you want to call it, it is in the memory, right? So, and why it's in the memory? Because it makes it really, really fast. Excellent. So great. So yes, so out of memory error, yes, will be one, and not suitable for large volumes of data. Right, right. So the biggest challenge with this approach is, in case you want to find the frequency of words in say 100 GB, and you don't have that kind of RAM available, then you cannot use this approach, right? Your RAM is hardly 4 GB, and 4 GB, a dictionary takes close to 4 times the actual memory. If your plain text is 1 GB, then dictionary will take around 4 GB to retain that text, because it has all sorts of internal overhead also. Now, and this memory calculation I'm talking in terms of Python. Java also has a similar kind of a overhead. So to store a data of one MB, the dictionary generally contains 4 MB kind of a space, right? So the biggest problem, okay, okay, not suitable for large volumes of data. Seeking is costly. That's Prasad. So see, seeking is not costly when it comes to dictionary, okay, because the all of the dictionaries or hash table are designed in order to make the seek really fast. Seek is independent of number of items which are there in the dictionary. That is the beauty of dictionary, okay. Seek is independent, it is O1, which means it is independent of number of items that are in dictionary, and that is why dictionary makes it a very important data structure in computing, okay. So seeking is pretty fast. Performance is poor. Performance is poor as in performance in terms of what? In general, this approach will not have a bad performance. It will be fairly fast. For all practical reasons, these kind of approaches are good. But the moment data starts growing, this approach does not work. Refreshing every time if hash table capacity increases, I think time complexity will be more. So generally when you talk about refreshing, say for a particular word, for we have allocated some memory and we are increasing the capacity, those are very well amortized costs, and they are very well designed so that the complexity does not grow beyond O1, okay. So you can have a trust on hash tables of these uh, programming languages, okay. You can trust the dictionaries because they are well designed, and probably this is probably 80 years old data structure, okay. So lot of research has gone into this. Good. So basically the problem lies in the memory footprint, okay, because we are putting all the data into the memory, okay. So that is the biggest problem. Now, if I have to ask you, what will you do in case you have to find the uh, word count for for a bigger data which does not fit into the RAM? Okay, RAM is generally very small as compared to your disk size. Your disk is generally in terms of terabytes, and RAM is hardly 4 GB, 8 GB. Okay, although in few systems those are expensive servers, people tend to put more and more RAM, maybe 100 GB or 200. But in general, the RAM is quite small and scarce. Now, question to you again is, what will you do? Okay, what will you do? Good. So Pratik says that if this approach is good with the smaller size of data, then we can again go with the distributed system thing, okay, where we can divide our input size, same logic at each node. Yes, very good point. But distributing a dictionary is a tough challenge. So you want to say that there are 10 dictionaries. So Pratik says that we could have a distributed thing, same thing but distributed. Some of the keys might be going to one node, some of the keys would be going to another, and so on. Right, Pratik? Now, at the same time, we'll have to maintain some sort of sharding mechanism and we'll have to build this solution. Keep a note of this answer and we'll get back to this one as soon as we are done. All right. So, for to building that kind of system, what Pratik is suggesting, it requires a little bit of sophistication. Okay. But let's try to solve it for few GBs. Okay. Because we can do it in multiple passes also. Right. We can do it in multiple passes also on the same machine. Yes. So thank you, Pavan. We can read only some lines at a time, like how merge sort do. Yes, that's also a very good point. So what Pavan is suggesting, and excellent solutions also. So what Pavan is suggesting, divide your data into, say, if you have got 1 GB data, just divide it into 10 parts. Maybe first, let's say that you have 10 files, and so you compute the frequency of each of these 10 files separately, and then you try to merge it one way or the another. Okay. Okay, that's another solution. We will keep a note of this one also. Good. So the second approach which somebody gave us, okay, saying that you split this whole book, whole text, such that one word should be there in each row, and do the group by word. Okay. So you break the books into one word per line and insert that one word from each line into the database table. After that, you do a group by on this one. So should you get the results or not? Is this correct? Is this approach correct to you? All right. Create a file. So next question answer from Tuntun is that create a file on the disk with every word name and put their frequency values. Okay. Okay. But don't you think that having if you have say 10 GB of 10 GB of text, having a billion words, having a billion files is good idea onto the files, although it's a creative solution, but having the billion words is a good idea. And also we don't have much to write inside the file because we just are storing a number. Frequency value is just one number, right? Okay. Okay. So the split would work on that much line. Yes, you're yes, Pavan. All right. So look at this approach and look at it closely. Okay. What we have done is we have taken each word from the database and then did a group by for that word and then counted it. Okay. Take a note of it because the group by is the very closest syntax to the map and reduce. The way in group by we define that this is our key on which you have to bring all group all the values together. Okay, based on our group by clause we group the input into various buckets, and then using our aggregation function we reduce all the values to a number, right? That's what we do as part of group. So we say group by word, so it's equivalent to saying our map has the key called word, and reduce is equivalent to saying count star. Think about it, and I mean we'll get back to this again, but this is a very good solution. So doing it in SQL is good because most of the memory issues SQL has already taken care of. So any sort, because databases sort and store the data far beyond the RAM size, right? And this would not give any memory problem, or will it give any memory problem in your opinion? Will this approach give any memory problem to you? Right? All right. So this is the second approach where we have utilized the database to do the job. Now the third approach is the Unix way. So how many of you are okay with Unix? How many of you are okay with Unix? Okay, Shashikant is one. Sushma is okay. All right, Prashant. Oh, great, great. So we have a great set of audience. All right, all right, all right. So yes, so Unix can be used, or these programs provided by Unix can be used to do the job. So all we did was first, so in a pipeline, we are building a pipeline below, and in a pipeline, each element basically gives out the output and also takes the input. So from left to right, each each command takes the input from the left hand side and gives the output to the right hand side. So cat file is giving the content of file 1 and file 2. Okay, cat command is giving content of file 1 and file 2 to anything which is after the pipe. This is the pipe, you see the vertical bar, this is the pipe to SED. Now SED is reading the data from file 1 and file 2, I mean the content provided by cat. Now what SED is doing is replacing tabs or spaces with new line. Okay, this syntax, this one is essentially like a control F with the regular expression, where we say that replace tab or space with a new line and then sort it and find the unique in the sorted data. So unique provide, I mean Unix provide you first a command which can replace the content line by line. Okay. Second, Unix provides you a sort command which basically sorts the data, and then Unix provides you a command called unique, which can give you the frequency analysis of a sorted data. Note that unique only works if the data is sorted. All right. Now here the syntax which you may not be aware is this part. Okay. Syntax you may not be aware is this part. Minus capital S1 gig. It basically says that sort using this much of memory. Okay. Sort using only 1 GB of memory. If you have only 1 GB of memory left, then you would use this syntax so that it does a disk sort for you. Disk sort as in it sorts one gigabyte of data, then puts it aside, then sorts another gigabyte of data, puts it aside, then sorts another gigabyte of data, and then keeps it aside, and then merge all of this data together and gives out the result. All right. So this is a very important command, and this would be very useful when you are dealing with little bigger data. Okay. So and I've used it multiple times in one of the my blog post where we were struggling with a problem in recommendation engine. The sort command actually helped us a lot doing the disk sorting. Okay. So basically, when you have to sort a data which is far beyond your memory, you generally use this minus capital S flag. Okay, the option minus capital S. All right. So this is clear to everybody, or should I explain it again? That how does it work? So the first command reads all the file 1, file 2, file 3. Then the second command replaces the space and tabs with new line. The third command sorts the data by 1 gigabyte at one time and then merges it. So sort command sorts the data using 1 gigabyte of memory, and then unique command finds the distinct in the input data and prints the counts. Unique minus C prints the count of each distinct word. Sounds good to you? No? All right. So we talked about three approaches. One programmatic, other scripted using SQL, and other shell script. This is a shell script essentially. Okay. Now, do you see any problem with the second and third approach? We noticed that approach number two, the SQL approach, and approach number three, both are really good. Both are really good in the sense that they successfully avoided the memory overflow kind of problem by using the disk. Do you see any problem with approach 2 and approach 3? Anyone? Okay. If the data is very big, then the computation is slow. Okay. Okay. Data being put in DB takes time. Very good. Okay. Again, not suitable for large data. Time factor to job. Yes. Yes. Unnecessarily making duplicated records in DB. Okay. Okay. These are very important points, and we'll make sure that we talk about it. All of these points. So we talked about three things here. First, the moment data starts going beyond RAM, the time taken starts increasing, and the following will become bottleneck. And that's what if you see uh, here. So here the RAM will not be an issue because RAM has been taken care of. But the network speed will become, the bottleneck, or disk speed will become the bottleneck. Okay, disk speed or the CPU will become the bottleneck. Okay, why? Because it's a single computer. We are trying to solve this problem, and it might, if the data is bigger, it will take a lot of time to sort on a single machine. Secondly, we are unnecessarily copying the data from one location to another. If your database is located in network, okay, or your local disk, or this data cannot have multiple copies onto the same machine because it's so huge. Say it's 80 GB data, and we want to create a database on the local machine. You might have to create a copy, and which is not possible, and therefore you end up copying it to the network database, and which might take a lot of time. Okay, so the network speed, disk speed, CPU, and disk space might become your potential bottleneck, although you have avoided RAM successfully at various points, right? So you basically, I mean, when we were not able to load everything into the RAM, we handed over the problem to the disk. And the more we did, I mean, so all of these things, when we are trying to read from the disk, so much data, so the disk will take a lot of time. And instead of CPU, the disk will consume most of your time. Okay, good, right. So effectively, cost of DB might increase. Okay, and maybe the DB is also not able to help you after, say, 1 TB of files. Unique in the Unix, the time taken will be more as it works sequential, but Unix provides you other kind of techniques using parallel. There are ways to actually make the sorting parallel. That sort command that can be made parallel, so that while one is reading from the disk, other is actually sorting. Okay, so I'm answering to Chetan Kumar. So there are ways to make that parallel so that it is pretty fast. There's a command called parallel in Linux. You can try that out. Okay. Yes. All right. So we are on the same page. Jatra is also saying the same thing. Good. Good. Now what? So, all right. So what then? We faced a problem with the various kinds of things such as copying the data. The disk will take a lot of time, and CPU, one machine may not be sufficient to give you the results immediately, right? So what do you do in this case? So as in the beginning, somebody was suggesting, I forgot the name, that we could use the same approach but multiple. So this is the exact approach we're talking about. He was talking about in the beginning. I forgot the name. All right. Yeah, I think Pavan only. Right. So yeah. So the approach which somebody suggested, or the approach which I'm going to take now is, we got multiple machine. We realized that one machine is not sufficing our need. Our data has grown to 100 GB or 50 GB, and we need to sort this kind of data. And so our local machine is not good enough. Now what do I do? How do I handle this? Okay, so how do I handle this kind of a scenario? So what I did was, bought one more machine. We got two machines now, and I wrote a script such that I sent some of the data to one machine, some of the data to another, and then ran the previous approaches 1, 2, or 3 onto these machine 1 and machine 2. Okay, and both machine 1 and machine 2 returned to me the these frequency table. And imagine that these machine 1, machine 2 are a network computer to you. Okay, for time being, for the or maybe machine 2 is a network 1 and you're operating from machine 1. So all you did was took your input data, divided into two portions, or if you have multiple machines, 5 machines, divided randomly into 5 portions, and gave the first portion to first machine, second portion to second, and did the approach first. I mean the approach number 2 and approach number 3 just now, which we explained. You used that approach to compute the frequency on each of the machine for each portion of the data. Now, as a result, all of these machine gave you the frequency table, that this word has come this many times, this word has come this many times, and so on. Also note that when we were dividing the data, we did not do analysis in the beginning. So what we have done is we just gave data, might be the words might be common in the two machine. Okay, like in this case, re ray is common at machine 1 and machine 2. Therefore you will have to put effort to merge these frequency tables. Okay, you will have to put efforts to merge these frequency tables, right? All right, and then we merged it and we got this output. Okay, does it make sense to you? We are trying to do a sort of a network, we call it a network sort, or we call it external sort. Great, great. So basically this is what we did. And note that when we merge this sorted data, these keys, these machine need to return this value frequency table ordered by the keys, ordered by the keys. Only then we'll be able to merge these frequency tables easily. Otherwise it will be very, very difficult. Okay, why I'm talking about this is because when you merge two sorted data, it's quite easy. You take the first word from both the one. Here I'll take re, and from this I'll take ga. Whichever is smaller, I will print that in output. Okay, which means ga is the one which has to go first. Now after ga is removed from this output, what I'll do is re will take its place. Now I'll compare re and re from both the sides. If they are equal, I'll sum their values and print in the output. So 2 plus 1 is 3. Now I'll read the next one and then print that one. Okay, it's like merging two queues of people who were already standing in ascending order of their heights. Okay, you have to merge. If you have to merge two queues of people who are already sorted properly, it's not a difficult challenge. Okay, but this challenge becomes a little bigger when you have, say, 20 queues of people who each of the queue is sorted by the height. If you have to merge such kind of queue, you will have to form a heap. Okay, you will have to form a heap of first the people who are standing in the first queue. Okay, and keep on taking the shortest out of that and keep on inserting the newer one from which the last person was taken. So heap sort is one thing which we use when we merge such kind of data, right? So Tuntun, you got your answer, because what I'm talking about is, so you have got A1, A2, and A3. or let me say A, B, F, G. So first queue contains A, B, F, G. Second contains B, F, F, H. Third one contains J, L, M, and so on. So the first thing you will do is you will pick up A, B, and J. You will pick up A, B, and J. All right. Out of this, you'll pick up out of A, B, and J. Whichever is smaller, you remove that from the queue. Okay. So this is the new line which I'm trying to create. Okay. Now you will again compare these three values and then see whichever is together, and then we can say that B has come twice, and then you remove B from both. All right, you remove B from both. Now you have got F, again F has come twice. You remove F from this. Now you are sorry, you will have to remove F, F, F. So it is three times. Okay, here F is twice. Okay, now so this is what you keep on doing until so you got G, H, J, and therefore F and G, then H and LMK. Sounds good. So we form the queue. So we sorted the data. We merged and sorted this data which was in three separate queues. Okay. To do this kind of approach, we generally form a heap, and we do this. We form the heap of the size of number of rows or number of elements in the first, the people who are standing in the front row. Okay. Right. So sorting can be parallelized in a very seamless manner. There could have been another approach where we, while reading the word itself, while reading the text itself, we keep on dividing it into many machines. So if we say that all the words which starts with K or below go to the first machine, and all those words which start from K above K go to the second machine, then we could have divided while distributing the data itself, and then we don't have to have the frequency table sorted, because we can just concatenate the two and then say that, hey, this is your output. We don't have to merge the results from two, because the words will be mutually exclusive. That approach could have been good, but the problem with that approach, in that approach we are basically dividing the data such that the data which went to machine 1 is mutually exclusive than machine 2. Machine 1 and machine 2 have totally separate data. Okay. Yes, heap is like a priority key. You are right, Pavan. Okay. So basically, heap is a data structure which is also used in priority queue. And yes, so min heap, max heap. The property of a heap is whatever element you add, you can take out the minimum in a log n time. And similarly, when you insert a new element in a heap, it takes log n time. N is the number of elements which are there in the heap. Good. All right. So this is what it is. Sounds good. Sounds good. So these were the kind of approaches we were taking before MapReduce paradigm came along. People were building these kind of solutions to solve their problems. Now, the challenge with this approach is, what do you think, there is any problem with this approach? Do you see any kind of a challenge with this approach? Yes. So Chetan says that as data grows, more systems need to bear it. That's correct, and should be the right approach. Merging will be complex for large data. Yes. So merging will take time, but merging technologies have been fairly improved. And merging does become bottleneck, but that can be solved. That merging itself can be divided, okay, by various techniques. So that machine 1 and machine 2, they themselves, try to merge, try to divide the data. Sorting might be expensive. Okay. Yes. Sorting. Yeah. So machine one, machine two, they will do the sorting i- parallelly. Yes. That will be expensive. True. But we have divided that task to multiple machines so that the work is done by multiple machines, because there is no other way to improve sorting than dividing it, because sorting algorithm itself is are fairly fast. If any file fails, any machine fails, loss of data. Very good point. Good. Let me make a note of it. Yes. So if any machine fails, then there will be a loss of data, which means you will have to build a solution which can take care of this failure, right? Which means we need to build a solution, and that is going to be very sophisticated. Okay. Good. 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 Any other problems do you see with this? This was external sort. We call it external sort. So one problem we discussed is that, right. So merge sort might be expensive. That is correct. And sorting might be expensive. And in case machine fails, the loss of data. So do you see any other problem? So when we were doing it, user sent the data to machine 1. Machine 1 did work on it, gave back the results. User also parallelly sent to machine 2. Machine 2 worked on it, gave back the results. So do you see any problem with this? User is sending the data to multiple machines, machine 1, machine 2, right? More time taken in the network. Excellent point. Good, good. Good. So the network is going to be our bottleneck. So the when we talked about processor, RAM, so we elevated in this problem, we elevated first three problems. So in this approach, we elevated in these approaches we elevated the problem of RAM. Okay, but we, and in this problem we elevated the problem with CPU by adding more and more CPUs. We added the problem with the disk by adding more and more disks parallelly, and and our RAM problem is also elevated. But the problem of network is still there, meaning we have to transfer a lot of data over the network, right? So that is the problem still left. That is the problem still left. And synchronization. Yes. So the main problem with this is, so synchronization, merge, merging of complex data, all of that I am putting it under would require a lot of engineering. Okay. Synchronization is a problem which can be solved by putting various kinds of flags, various kind of techniques. But that would require a lot of engineering. For each problem we would have to do this kind of engineering. Okay. So and second, time consumed in network is becoming still the bottleneck. For each requirement we need we would need to uh, we need to build a special purpose program, right? So there is a lot of engineering required. There's a lot of engineering required. So, so exactly all of these problems, some people did a lot of engineering upfront and built a generic solution for us, that is MapReduce of Hadoop. Okay, so MapReduce is essentially a big group by clause, a big sorting mechanism for you. Okay, and other than providing you a lot of machinery, MapReduce also exploits the fact that data is already distributed. So whenever you want to work on data, data is already there on multiple machines. Why? Because each data node stores the data, right? So both the problems, transport of the data, initial transport of the data, as well as the engineering part is very well taken care of by MapReduce. Sounds good to you? All right. So I've gone step by step into demonstrating that how do we generally solve the problem. The history of computing has evolved in that manner. Okay. History of computing has evolved in that manner. In the beginning, our problem was RAM, and after a point of time, the problem became disk, and after a point of time, the problem became the network, and and so on. Okay. And all of this problem occurred because data kept on growing. Our requirement to handle the data keeps on becoming bigger and bigger, right? So, so exactly to solve all of these problems, some people came up with a mechanism called MapReduce. They thought that they have written this external sort. They have written this great external sort of this diagram. They have already written it, and then thought that they will share it with the world, and that's why the Google published that paper called MapReduce. Okay. Now, for the massive parallel computing is parallelly getting the work done on multiple machine. Distributed and parallel, there is a very thin line between distributed and parallel. Parallel means also on the same computer, but different CPU. Each computer can have different CPU. So that's when you are executing instructions on these different CPUs and trying to divide your work. That's also called parallel computing, right? The Unix command called parallel actually does a parallel on the CPU as well. Okay. Now, so MapReduce is essentially a programming paradigm. It's like a function provided to you. It's like a syntax provided to you, and it helps you solve these kind of big data problems. And as I has explained to you earlier, sorting is the holy grail of processing. Most of our processing, most of our processing problems are essentially sorting problems. Okay. If your problem is not a sorting problem, then there is a far more to it. For example, finding a path in a map from one side to another, from one point to another, could be broken down or could be simplified by sorting the data points. Okay. So similarly, lot of problems can be solved, can be made easy by using a sorting algorithm, by sorting the data. Okay. So, so specifically sorting intensive jobs. All right. You have to code essentially two functions. One is called mapper, other is called reducer. I'll be using map and reduce and mapper and reducer interchangeably. Don't get confused. Mapper or map is a function which basically converts input into key value pairs. We try to break down our input into key value pairs such that it solves the problem, just like in a group by clause. So map reduce is essentially a grand grand group by clause. In group by clause, we specify the sort by this particular field, and then we say aggregate by count. Okay, so similarly, MapReduce is essentially a great grand you know group by clause, just that each group by the selection of key can you can write a program there. Okay, when you are building a selection of key, say for example your input data is something and you want to select a key which is uh, say root of your first column, or concatenate first two columns and then inverse the concatenated value. Okay, so that kind of formation of the key for doing our group by is possible. Okay, I mean that is the flexibility MapReduce provides us, because you can write mapper or map as a as a function in your own choice of programming language. Okay, own choice of programming language. By default it is Java, but there are libraries which help you writing the writing the program in the program, writing the mapper or reducer in the programming language of your choice. Okay, so mapper essentially converts the input into key value pairs. Okay, reducer aggregates it. Okay, just like we did a group by, we picked up a word that group by this key. Similarly, mapper essentially says that group by this key, and this is going to be my value, which need to be grouped by. And reducer essentially takes all those values, okay, which are aggregated together by the whole paradigm. Hadoop will take your these two functions, run mapper on each input. Whatever output comes in, it will sort it, and for each key, all the values will be put together, and these values will be fed to your reducer function, and then it will give out the single value for that. All right, sounds cool to you? Okay, now let's just demonstrate a very simple word count program. Looks like everybody is doing, the whole industry is using only the word count as an example. We'll go into more sophisticated examples after this. All right, so imagine that your mapper function, the one which is converting the input line into word, looks like this. This is a pseudo code. Don't try to think of it as javascript or anything. Just it's a pseudo code. Okay, so we are saying for each word in this line, okay, input is basically a line here. Okay, so each of the line in the input is given to your map function, and here this is your code. This is the code you have written or I have written, where I say that for each word in the input, print word and one, word and one, word and one, meaning word is our key and one is our value. Okay, word is our key and one is our value. All right, now once I'm done with it, what I'll do is, okay, we wrote another function called reduce, which essentially provides you two parameters. This function has two parameters. One is word, other is array. Okay, the word which you gave out here, and here's the array, and all you do is you sum it up. Okay, so this was your input line. Okay, this was your input line. For this input line, this is what you created. Per line there is a key and the key and the value. This dashed line is essentially this whole transformation is done by Hadoop for you. This transformation is done by Hadoop for you. Hadoop took your content key value pairs and then sorted it and then grouped all your values together. So sa has come twice. So 1 comma 1 is the value provide the sa is having. Okay, and then for each of these key, which is going to be distinct, of course, your reduce function is applied. So sum of 1 is 1, sum of 1 is 1, and sum of 1 comma 1 is 2. All right? Sounds okay to you? No? All right. So this the dash line represents the transformation done by Hadoop for you. Okay. Now the next step is like this. Okay. Here it's a single reduce. It just looks a little weird because I've tried to temper it. All right. Now it looks good. All right. Now, this one was just a diagram which showed you a single process. Now, this is what is going on. Say you have got two computers, two data node containing one block each. And for just example reasons, I'm saying that there are two blocks. Each node has one block. And this first block contains sa, re, saga as the line. These are the words in the line. And the second node contains sa, re, sa as the uh, as a only single line. Now, on the node 1, your map function, which we demonstrated in the previous case, will produce this output. Okay, it will produce this output: sa1, re1, sa1, and ga1. And on the node 2, the output that is going to be produced is sa1, re1, sa1, right? Which means which means we have created the key value pairs just like using this function, the function which presented in the previous session, previous page. Now, after Hadoop does the sorting, first Hadoop will do the sorting and then do the merge shuffling. So after the sorting happened, Ga came first, then Re, then Sa came together here. Similar thing happened over here also on the right leg. Here, this right leg. Ray came first and Sa and Sa. And once the merge and shuffling started happening here, here this fourth is here, okay, and fifth is here, okay. Once the merge and shuffle happened, okay, so Ga came Ga is 1, right? Because Ga is only on the one side. We are trying to merge these two. Okay. Ray is 1 comma 1 because it's on the both side. And Sa is 4 times 1 comma 1 comma 1 comma 1. Now, now the thing is that once this is done, reduce function will be called on this output produced here. Okay, this fourth step, whatever the input is here, for each of the key your reduce function is going to be called. So array.sum for 1 will result in 1, array.sum for 1 comma 1 will result in, let me just make it a little correct, okay, will result in 2, and 1 comma 1 this will result in 4. Okay, okay, so we'll talk about, so merging is clear to you, it's just the shuffling keyword is bothering probably, right? So I'll show you this part. So basically here the shuffling keyword would be bothering because merging is okay, I believe, right? So just give me a little time. So now question to you is, instead of, had your reduce function been array.count, okay, array.count, would the result still be same? Instead of array.sum, had it been array.count, would the results be same? Array.count essentially does is counts the number of elements in array. Okay. Chetra says no. What do you think the output could have been here? Satyanarayan and Chetra? Were had we our input, this function could have been array.count. What could have been the output here? Yes, both will give the same results in this particular case, right? And that also means that even if we print something like here xyz instead of 1, instead of printing 1, and we would have 1 xyz here, okay, and it could have been still the same answer, right? Let's say we had this here and here and so on here also in the same manner. That also will give you the same answer, right? Array.count, right? Just to bring familiarity to this syntax or this mechanism, I'm trying to do a little bit of changes, right? All right. So conceptually, the MapReduce is clear. MapReduce is essentially, after giving it a lot of thought, I figured out that MapReduce is essentially group by clause. Okay, where we say group by this element and apply this that reduce function on our values. Okay. Now here there was a single reducer. Reducer was singular. Okay. Reducer here was single. Now what happens in case the reducer is multiple? Okay. So the important part here is this point where you see the in the third step, do you call MapReduce group by or just reducer? No, no, MapReduce whole thing is a group by, because see, the map phase is equivalent to saying group by this function, right? While reduce is equivalent to putting count star in your syntax. Okay, whenever we say group by, right, group by has two parts. One is aggregate function, other is selection of the key, right? All right, right. Yes, yes, you got it correct. Right? So if you have used the group by, you would be able to quickly correlate that, hey, this is the same thing. And now I can break my problems into meaningful things. Yes. So shuffling will be used in multiple reduce, of course. Okay. So basically in shuffling, what you need to do is you need to bring the keys together. Okay. You need to bring keys together. The result should be same. It should not be the result is different. The result should be same whether you use one reducer or multiple reducer. All right. Here, after the merging and shuffling happened, so at the step 3 we has ga, re, sa, re, sa, right? Now when we did a shuffling, so the sa from one side went to the other side while re came from right hand side to the left hand side, right? These two SAs went to the right hand side while Re came to the left hand side. Now Ga Re came to the left hand side, okay, while Sa went to the right hand side, okay. After that, your reducer will be applied equally on both sides of the wire. For each of the key, rest of the process will remain same. Okay? You just have to tell Hadoop that, hey, I want these many reducers, and it will create these and many reducers of your choice. And this division of data, that which key will go to one reducer and which key will go to another reducer, is also configurable. We'll go into the details very soon. Okay. The shuffling happens on the reducer side. No, shuffling happens before the reducer. Okay. Shuffling happens before the reducer. Generally what happens is, in the during the map phase itself, each of the data node, or each of the node which is doing the map, will keep the keys separate. Okay, if you have three reducers, the map itself will keep the three portions of the data, and then each map will do the three transfers to all the three reducer. Okay, so that's how it happens. Yes. Okay, Satyana's question is, grouping similar values under same key come under merge. Yes, you can say that. All right. Now, Prasant's question is, programmer cannot configure the number of mappers, but he can configure the number of reducer. Very, very true. Very, very true. So far, the Hadoop has not provided you the number of choosing number of maps, right? Number of maps is basically decided where is your data lying. If your data is lying only on two nodes, the code of your mapper will be sent to only the two nodes. Like here, whatever code you wrote went to the node 1, as well same copy of the same code went to the node 2. Had they had your data, this data which we are you are operating upon, so before starting to work on a Hadoop, you have to tell that, hey, this is my map, this is my reduce, and my input data is this. So now Hadoop knows that your files, the name node knows that these files which you want to operate upon exist on this data node. And then it will run your mapper on all those data nodes. And after it has done the processing on all of these data nodes, it will try to merge it, then run your reduce function. So mapper is dependent on where is your data lying, while number of reducers is dependent on what you have configured. And sometimes the client itself, say pig client, while converting the query, they themselves specify how many reducers do you want based on sampling of the data, right? So reducer is configured by you, while mapper is decided by Hadoop. When we do group by when we do group by, what exactly aggregation happens in mapper or reducer? Okay. um okay, let me, so Chetra, could you repeat your question, because I need to again understand it. Let me try somebody else's answer by the time you repeat. If we set the value of reducer to 0, what will happen? Is this case valid? This case is very valid. Yeah, you can have map reduce phase without a reduce. Okay. Once reduce happens, okay, once reduced happened, then there is no merge or shuffle. No, after the results you have received here, the results have come. There is no need of, there is no shuffle or anything. So here there will be two files essentially, and there will be two different files. If you want to operate on both the files, you can concatenate them together before running your next set of MapReduce or running next set of programs. Okay. So here you must be thinking that there are two files now, Gay1, R1, Ray1, and Ga1, Ray1, and Sa4. These are two files. This one goes into one file, this one goes into another file. Now, but if you want to you can straight away concatenate them and start processing in the next process. Okay, in the next process, or you can write your program to just concatenate them and upload it somewhere. Okay. Yes, right. So Purushottam, am I able to answer your question? Pawan's question is it bringing business data towards logic? Yes. So if you see, node 1 did not move the data, but it took your map function. I mean, Hadoop took your map function to the data, applied there, and then the transfer happened after the processing happened. Okay. Before that, I mean, generally what would we do is we'll read data from node 1, node 2, bring it to one computer, apply our logic, then put the data back. And that is the biggest difference. Because transferring of say a terabyte data itself takes close to 3 to 4 hours over the network, or more than that actually. All right, now let me take your questions. So merge, it merges data based on key. Shuffle, sending the merged data towards the reducer. Yeah, your understanding is correct. So merge and shuffle is generally used interchangeably, the keyword, and we generally say it together that we are trying to merge all the keys together and then shuffle back. If you see, we first try to merge this data input and then split it. So although this strategy has been changing quite often, okay, because sometimes when you do merge, when you have multiple reducers, the mapper itself divides the data and sends only a portion of keys to one reducer and other portion of the keys to another, and another third portion of keys might be sending to the third reducer if there are three reducers. So this merge shuffle phase is just a hypothetical scenario for the understanding. The strategy has been changing a bit. I'll show you a couple of more diagram. You'll understand it when I describe how to build a combiner, how to build a splitter. All right. What is the logic behind shuffle? Like how different map outputs are assigned to different reducers. Okay. So in the shuffle, basically we are merging this together and arbitrarily some of the keys go to one machine, some of the keys go to another, some of the keys go to some other reducer. If you have two reducers, so arbitrarily it is decided. Also, this is something you can also write your own function partitioner, which will help Hadoop deciding that which reduce will get which keys. Okay, which reduce gets which keys. Once we sort the data, where exactly where exactly aggregation happened, right? Aggregation happens on the nodes which are running the reduce function. The nodes, the computer, it can this node can be one of the data nodes, or it can one of the data nodes containing the data, all or also it could be a third node which is free at that moment of time. Okay, which is free at that moment of time to do the processing. Generally, a node which is free in terms of CPU is assigned to do the reduce. Okay, I hope I got your question. If user set okay, no, there will be no reducer that will run. Okay, in Hadoop, which component feature is responsible for merging and shuffling? Okay, okay. So in Hadoop, basically the whole, if you look at the Hadoop, there were HDFS, there was HDFS, which actually stored the data. Hadoop is essentially this whole algorithm of sorting the data and shuffling the data. That algorithm and applying these functions. That whole MapReduce is about this. Okay. So basically MapReduce's job as part of algorithm is merging and shuffling. Right. Good, 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 good. Very brilliant questions. All right. So it's analogous to group by, as I said, right? So the way you can everybody get it, right? Or is there a doubt? I put different colors into different one. So the one which is darker one, which is map. Okay. So this is analogous. It's an analogy. Okay. All right. Good, good, good. So now my question to you is, all right. So today I'll have to leave you with the problems. Okay. I want you to work on these problems so that we can discuss it on Monday. Okay. On Monday, because I need you to work on it, these all these four problems and think about this, and then we can have the discussion. Okay. I'm leaving today in the first half itself. Okay. After describing you these four problems. Okay. And then you, because what I want you to do is I want all of you to finish this assignment before we go forward. Otherwise it will be, it will not be fair. Okay. Otherwise it will not be fair. Okay. So do not worry about the time. Everything is going smooth. And okay, as part of program, I want all of you to go through these problems and understand all the four problems before we finish today's session. Okay. Instead of one reducers, we'll take two reducer. Okay, okay, good, good. Let me answer Susma's question. Instead of one reducer, we'll take two reducers. How exactly it works? Okay, this one. So in this one I was describing that when we had one reducer, okay, when we had one reducer, there was no shuffling, there was only merge. Okay, there was no shuffling, right? So if you have multiple reducers, the keys are shuffled. Some of the keys from are sent to one reducer after merging. First merge will happen, then shuffle. So or sometime, I mean, these days, from the map itself, here the map itself, while it is sorting the data, here directly the data starts go that data starts going to reducer. Okay. I mean, we'll discuss that one also. So instead of reducer, we'll take two reducers. How exactly that works? Okay, okay. So basically, if you have two reducers and say there are 10 keys and each key has some values, some of the keys will be sent to the first reducer, some of the keys will be sent to the second reducer, and then on each key one by one, the function called reducer, the one we have written, okay, the function we have written will be applied onto these values, and reducer will convert our function which we have written, reducer will convert these multiple values into single value. All right, Susma. Okay, I need to understand more. I need to understand more, and I would love to explain it. So in this picture, the result of fifth one, yeah, it's not merged. It just for the uh, example purposes, it is in the it is shown as a single file. Okay, ideally it will be file one. We call it part one. File one is like this. Okay, and file two is like this. Okay, Sasikant, did I make sense? All right. Now, okay, let me describe these few problems to you. And Sushma, I would like to understand actually that which where did I confuse? And yeah, go ahead, Sasikant. So let me describe the problems while you note down your doubts. And after I describe the problems, we'll take the question again. Okay. Now, or you can file one and file two will not have the same key. No, there will be no key common in file one and file two. Meaning, one key cannot go in the two, both the files. Okay, because what people think seem to think is that some of the values of key one go to one, some of the values of key one go to another one. No, that's not that happens. Okay, yeah, ask the question please. I'm waiting. File one and file two will never have the whole promise. This thing is doing the whole promise Hadoop makes to you is your reduce function will get all the values for a key. Your reduce function will get all the values for a particular key, no matter on what nodes this data exists, no matter where are the keys existing in the input, whether a key is existing in all the data blocks or whether the key is existing is the output of all the nodes. Okay, so if there is a single key, imagine this, if there is a single key and you have configured that we have got 10 reducers in this example, imagine that you had only one key, one input, there was only one thing called, there was a file called san only. There's a single word it contains, that's all, it contains only one word. Now what you did was you wrote a mapper and reducer the way it is right now, and you said reducers equals 20. You have 20 computers. Okay, that does not mean that there will be 20 places, or you imagine that there is a single file containing these words. Okay, these words, 20 times. Okay, 20 times. So there will be only single file, file 1, containing sen, and it will say that it has its frequency is 10. Okay, it will not say, file 2 will not have anything, file 2 will be empty. Okay, there'll be there'll be 20 files, but all 20 files, 19 files will be empty and one file will contain all of the key, all the 20 number. And imagine that this data is spread across let's say same key repeated many times. Okay, here it is repeated. Okay, so I'm trying to duplicate the data here. Here the same key is repeated how many times? 500 times, 480 times. Okay, and it is located on say 10 nodes. This file is split it into parts and is located onto 10 nodes still. And you have defined, so mapper R10 and reducers R20, and still there will be a single output containing single file containing sen equals to 20. Okay, not 20, it will be 480. Okay, let me, so we say sort and we say unique minus c, it will be 40 and sen. Sounds good to you, Pavan, Sasikant, Pratik? All right. So no matter what, the a key and its values will be passed to the reducer at a one time only. One key, reduce function will be executed only once for a key. Great. We'll give you, you should, when I give the word count example in the next session, right? Or anyway, I have opened up my all the sessions. You can actually have a look at the even the project we have. Okay, Java project we have. You can experiment and try to put more reducers and try to duplicate the data on our nodes onto multiple nodes and try to understand that how is it working. Okay, you try to simulate what I have just tried to demonstrate to you once we have once you go beyond today's session. All right, sounds good to you? All right, let me close this. Good. All right, if you want I can give you show you the where is the project located. You can use that one and then you can go ahead. All right, now, so here if you have www.nobigdata.com, my courses, and we have 14th January, and out of this we have got session number 3. Okay, presentation assignment for sample project. So this is the sample project you can download, and and then you can work on that. Okay, download and just configure it in Eclipse. All the libraries are available in that project itself, and then you start working. Okay, so basically there if you are able to run, I'm just skipping ahead because there are 2 days of holiday. You can try it out when you are free. Okay, all right, so now let me get back to the question and let me challenge you a bit. Okay, now first one is, first question to you is, if you have to find the frequencies of letters instead of words, say you have to find frequencies of only alphabetic letters, you have to ignore numerics, you have to ignore any punctuation or special characters. All you have to do is give the frequency of letters. Okay, and only A to Z. Convert the uppercase to lowercase, and capital A and small a is equal. So you have to tell me the frequencies of letters. Why do we need frequency generally? Based on the frequencies of a letter in a sample, you can easily predict, you can easily predict which language is it, what kind of a language it is it Hindi, Devanagari, or is it English? So just based on the frequencies of the letters, we can quickly predict the nature of the text we are processing. Is it a mathematical language? It is whatever. Just based on the frequencies of the letter, we can predict a lot of things. Okay. So given a text, given a huge text, humongous text, okay, in GBs, you have to find frequencies of letters. Okay. So can you tell me how big the output is going to be for this exercise? Quickly, anybody? If 26 numbers, right? Yeah. It is going to be an array of integers of 26 length. So for this kind of a work, though the input is maybe 10 GB, okay, maybe 10 GB size. Now, do you need this sophisticated map reduce for this? Yes or no? Please write your reasoning. Please write your reasoning, and you can write the reasoning over here. You can write the reasoning here. You can take this session and you can write your reasoning. Okay. All right. On the website, if you go, you can see the subjective test. Click on that and you will see. Now, do you need a map reduce? That is my question. If yes, then what is going to be your logic? I want to see that. Write that also. Okay. So you write your logic of map reduce in also after you have justified. Okay. I mean, even though you may not agree here that map reduce is required, still just write a simple logic, as in your own plain text or any pseudo programming language. We are not looking for a code per se. Okay. Now the second problem is you are given a huge text. Okay. You have to find anagrams in it. What does it mean by anagram? Anagram is basically different arrangement of letters in a word. Okay. Say for example, cat, take, and act are anagrams. Okay. They are not just reverse. Reverse is called palindrome. Okay. They are anagrams. Okay. All of the these are basically rearrangements of the letters in a word. Okay. So given a huge text, you have to find the the word the word which are anagram of each other. How will you do that? Find the anagram of the words. All right. So in this text, you can see cat, take, and act are anagrams, while the, to, in does not have anything else. So what I expect, we want to just bring the anagrams together, and those which are single words which does not have anagram, let them be alone. Okay. So we want to group the anagrams together. Okay. You can see that THE does not have an anagram in the input. Okay. Very good. Very good. Okay. Okay. So if you have to do this, you have to do it in MapReduce, Prashant. Okay, you have got a humongous text. Okay, you have got humongous text of few GBs or few terabytes, maybe 2 terabytes. Now you have to find anagrams of each other. Okay, but your approach is correct. So you have to tell what kind of logic will you write in maps so that all the anagrams can come together. Good. Now next question to you is, there is a file that contains the DNA sequences of people in this format. Okay, there is a user one whose DNA sequence is given. ACGT is the DNA sequence, and so on. All right. Now, what do I want is bring all those people together whose DNA is exactly same. whose DNA is exactly same. For this case, user 1 and user 4 are the same DNA, while user 2 and user 6 are do not have any other user which has the same DNA, and while user 3 and user 5 have the same DNA. You can see that. So you have to bring those users together whose DNAs are identical. Is these two are these two problems anagrams problem clear to everybody? Anagrams problem is okay with everybody? Good, 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 good. And the DNA problem? DNA problem? All right, all right. So good. So now the second part. This is fairly simple part. I'm not going to read out anybody's answer right now. Okay. You please fill in that in the subjective test. Please provide this, and then we will discuss it. Okay. All right. Now, second part of the problem is a file contains DNA sequence of the problem people. Find all those people who have same or mirror image of DNA. Okay. No, no, you don't have to write Java code. You just have to write pseudocode. Even if you write in any way, you just have to tell me what has to be the map, what has to be the key for the map, and what has to go in the reduce function. Okay, how will you what how will you create the key for the map? And while you are at it, just write in your plain language that map will produce this as the key and that as the value. All right, that's all I'm looking for. As well as you have to tell me the in the reduce, these are the things we are going to do. Okay, in your plain language. Okay, you can write SQL also, but yeah. Okay, all of this data we are talking about, except for the first problem here where we are doubting whether do we need to use map or reduce. For rest of the problems you have to do it in map and reduce. Anyway, do the frequencies also in the map reduce, please. Okay, do we need map reduce? Whether or not, please write the code. This will be useful for all of us. All right, now here second problem is, given the same input file of user and the DNA. Okay, so right now this sample data is not located anywhere in the file system. Okay, but for the problem sake, the data is located in database. All right, and then you have to do, but right now it's more or less a conceptual problem. You just have to, we don't have a dummy data right now, but you can create the dummy data using this input. All right, you can create the dummy data. All right. So this file 3b, I mean in this, contains the DNA sequences. Now what you need to do is you have to bring the users together whose DNA is either same or the mirror image of one another. The mirror image of one another. You got the problem? See here, user 1, user 2, user 4. User 1 and user 4 have identical, while user 1 and user 2 have exact mirror image. ACGT. If you go from right to left, left right, then okay. So you have to, given this sort of a data in gigabytes or hundreds of gigabytes, you have to bring these users together whose DNA is either identical or mirror image. Sounds good to you? What is it that would go in map and what is it that will go in the reduce? All right. Now the fourth problem, fourth problem is, it's a little difficult one. It would require multiple map reduce passes. Okay, so when you are building this, you just write down in theoretical way that is going to be in the first pass and second pass, and this is the map. This is a key for the map in the first pass, and so on. Okay, so in this unusual democracy, everybody is not equal. Okay, there is a country where is this strange democracy where the rich get the vote of rich has more value than vote of the poor. Okay, the vote count of the rich has got more value than the poor. So, and people are voting to each other. Okay, so A votes for C, B votes for C, C votes for F, and we know their worth. We have their list of worth from the bank accounts. A's worth is 5, B's worth is 1, C's worth is 11. So C was voted by A and B. Therefore, C's worth becomes A plus B, which is 6. The vote count of C is 6, right? Similarly, F was voted by C and C's worth is 11. Therefore, F's vote count is 11. And A and B has got 0 vote count. Okay? Sounds good to you? Is this question clear to you? So what you need to do is, given list 1 and list 2, given the worth as well as who voted for who, you need to tell me the what is the vote count at the end of the whole election process. You will be given these two files, one containing this list, other containing this list, and you have to give me the results. One containing the votes, who voted for who, other containing the worth of each individual, and you have to tell me the resulting vote count. All right? And this is for billions of users. This is for billions of users. For those who are wondering why am I portraying such problem, this was the problem for which the map reduce was actually designed. This is similar to the page rank problem, but not really as complicated as the MapReduce, sorry, PageRank is. Okay, PageRank is the way Google computes the rank of each pages. Okay, but don't get confused. It's not that complicated. It is far more simpler. Had it been your simple SQL, you could have just put a join between list one and list two, and then did a group by. Okay, it could have been as simple as that, right? So you need to figure out how will you solve these four problems using MapReduce. Write down in a plain English that my map is going to give out this key and this value, and my reduce is going to take these values and going to combine this way so that the result is this much. Okay, sounds good to you? All right then. So that's good enough for today. Rest of the things we'll take up on Monday. Finish all these four questions by Monday. And if you have any questions, any problems you face, just drop me an email and then we can discuss it further. Okay. You have got 1 more hour left for this session. In this 1 hour, maybe you can finish all the four questions as well as finish the objective test provided here. If you go back to the course page in the first session, you have this quiz. Please finish that because not many people have finished it. Only few people have finished it so far. All right. So finish the first quiz and finish the this subjective test, and then we'll talk about things. Okay. All right. Thank you very much. Have a good day. Bye bye.